Hello class, welcome to this lesson on Newton's first law of motion. Today we should be able to define inertia and relate it to Newton's first law of motion. So first we have to define inertia, we're going to define Newton's first law of motion, and then I'm going to give you some examples of how that applies. This is going to be a total conceptual lesson, no math involved. So if we look at our definition here, inertia, the resistance of any object to any change in its motion. Some people have even called the laziness of an object. The laziness of an object. And really that's come from the fact that objects don't want to change what they're doing. They're, in essence, lazy. Objects at rest want to stay at rest. Objects in motion want to stay in motion. So this is where we get Newton's first law. Newton's first law. And Newton's first law basically redefines inertia, but it does add one important piece. So Newton's first law, any object will resist change in its state of motion, and here's the big one, unless acted on by an outside force. So, to give you an example, I have my pencil right here, and I can take this pencil and roll it across the screen. I set this pencil into motion. So, according to inertia, our Newton's first law, this pencil should keep on staying in motion. Why is it stopping? And the reality is it's stopping because it is acted on by an outside force, which is friction from the pencil to from the pad of paper here. So this is why if you were, say, in space and I took this pencil and I threw it across the way, it would just keep going and going and going because there is no outside force, there's no source of friction to keep it, to stop it from moving. So all objects will remain in their state of motion unless acted on by an outside force. Things that want to stay in motion, and things that are at rest, stay at rest. And so here are some examples. First one is my bike example. I'm going to draw a very awesome bike here. Okay, bike and a very, very elaborate rider. And someone on the bike is cruising along and they hit a dip. And the front wheel gets stuck. And this person will then be launched off the bike, sailing through the air. Okay? And notice, think of the words I just said. This person is launched off the bike. This person is thrown from the bike. And the reality is our language makes us think, it gives us a misconception about what's really happening here. Because our language will say, oh, he was thrown from the bike. But the reality is, this person, this object, was in a state of motion. It was traveling along with the bike. It was traveling along in this direction. And the bike stopped moving because it was acted on by an outside force, which is the pothole, the dip, whatever you want to call it. And this person who was on top of the bike, he or she had inertia, and their inertia kept carrying them forward. So the bike didn't throw the person off. The person just kept on going however fast he or she was going before the bike hit the pothole. So the bike didn't throw the person just kept on going. The same goes for a car. Now, I don't mean to be insensitive here, but if a car is in a head-on collision, person in front of the car, and this person, we'll say, hits a wall here. Okay, this person hits a wall. And if they are not wearing their seatbelt, they will continue to travel at the rate they were going beforehand. So let's say a car was going 40 miles an hour. If this car was going 40 miles an hour and this person was not strapped into the car, i.e. a seatbelt, the car stops and this person just keeps on going 40 miles an hour. This person is not being thrown from the car or launched out of the car. They are just continuing their state of motion. The car was going 40 and it stopped. The person was going 40 and he or she kept on going 40. There is nothing stopping that person from going 40, so they're going to keep on going through the window, which is how we get, deadly accidents. Wear your seatbelt. Another example, was something you haven't thought about probably, is the Earth example. The Earth example. Right now, the Earth is spinning. Right now, the Earth is spinning. And just for ease of a picture here, we're going to assume here's my classroom, and here I am talking to you to make this awesome video. Well, this Earth is spinning, and we're going over 1,000 miles an hour. We are rotating 1,000 miles an hour. How come, if we are rotating 1,000 miles an hour, when I jump up, how come this wall will not come crashing into me and just knock me out? And the reality is because the Earth is spinning 1,000 miles an hour, or 1,000 miles an hour or more. The classroom is going 1,000 miles an hour or more, and I'm going 1,000 miles an hour or more. We all are. So the reason the wall doesn't come crashing into me is because we are all traveling in this state of motion, and there's nothing to stop us from traveling in a state of motion. So the reality is, if I jump straight up or down, or you jump straight up or down right now, you are in the realm of space. You are actually covering a distance, but you don't feel that because the floor that you jumped off of is still directly beneath your feet. So you don't think you're changing anything, but you really are, because while you are traveling, so is the floor beneath you. So the reality is, when I jump up, I land over here because the Earth and myself move, but the classroom is still exactly right where it was before, so it didn't feel like I didn't move. So once again, I'm in a state of motion. Nothing is stopping me from being in a state of motion, of rotating around the top of the Earth. So therefore, I stay in a state of motion. And one more is the plane example or the car example. If you were sitting in a plane and you tossed a coin up in the air, once again, if the plane is traveling forward at 700 miles an hour or however fast planes travel, how come the coin doesn't go screaming to the back of the plane? Because the coin is also going 700 miles an hour along with your body. So if you put the coin up in the air, unless there's something to stop it from going backwards, it's going to continue going forward, because any object in motion will stay in motion, and any object at rest will stay at rest. On a side note, this is also a good reason that you should study when you first get home, because once you sit down at home, we call it mental inertia. Once you sit down and you are at rest, you are not going to ever want to not be at rest. Students at rest want to stay at rest. And so there's a lot of mental inertia there to get from a state of rest to a state of motion. There has to be an outside force, outside discipline, outside motivation, whatever, to get you moving. So it really is beneficial for you to, if you're at school and you're working all day, to go home and to keep it going, because a brain thinking will remain in brain thinking over a longer period of time. And so get it done and then go to a state of rest once you are finished with it. So anyway, Newton's laws of motion. So this is also known as the law of inertia. Okay, thank you.